Okay, so now we have some tips on how to solve problems involving forces. And we want to follow the same procedure as we've been following for any kind of physics problem. First, we're going to draw a sketch. Then we're going to identify what you know and what you do not know. Then we're going to draw something called an FBD. That stands for free body diagram. This is where you identify in your sketch where all the forces are acting, each direction where the force is actually going. And a little hint, if you're on an incline, then you're going to want to rotate your coordinate system. And we're going to show you what that looks like in an example. Then, once you have all your free body diagram drawn, you want to write Newton's second law in both the x and the y directions and start doing algebra. This is going to look something like the sum of forces equation equals mass times the net acceleration, or you'll have sum of forces equals 0 if your acceleration is equal to 0. So let's see how some actual examples work with this. So let's start with the basic problem of how we can actually use forces. First, what we want to do is calculate the force. So we want to get the force that a 70 kilogram high jumper must exert on the ground to produce an upward acceleration that's equal to 4 times the acceleration due to gravity, and explicitly show the steps you follow, how you follow the steps in solving problems for Newton's laws of motion. So how do we actually do this? How do we start approaching? First, we want to draw a picture. So we're going to draw a high jumper. We're going to draw a picture of just a person. So here's my person, and my person is not a very good high jumper because they're just a big blob of circle. So I'm going to have two forces that are acting. First, I need to calculate the force that a 70 kilogram high jumper must exert on the ground to produce an upward acceleration 4 times the acceleration due to gravity. So I'm going to push down, but I'm going to have a resulting force of that jump that's going to result in me moving up. So that's going to be the force of my jump. Now if I look at what other forces are acting on me, I'm drawing a free body diagram, I'm drawing a picture of this. The other force that's going to act to pull me back down to the ground is going to be the weight, the force of gravity, which sometimes you'll see labeled as W, sometimes you might see this labeled as F sub G, the force of gravity. They're both representing the same thing. We're told that the mass of this jumper, if we're going to write all of our knowns, is equal to 70 kilograms. And we're also told that our total acceleration has to be equal to 4 times the acceleration due to gravity, which we know is labeled as G, typically, where G is equal to 9.8 meters per second squared. So if I want to take this problem further, the next step would be to write the sum of force equations in both the x and y directions. Now in this case, I only have this guy is moving up and down, so I only have to worry about the y direction. So let's write down all the sum of forces in the y direction. Sum of forces in the y direction. And that's going to be equal to whatever force is acting up. And I see that there's the force of my jump that's acting upwards. I see no other forces acting up, so now I can subtract the forces that are acting down. And the forces acting down I see are the force of gravity, which we can label as just the W. And that's going to be equal to the mass times the total acceleration in this system. So I can start working with my equations. I can start expanding out my force equations. Once you have your force equations, that should be enough information to actually solve the problem. I'm looking for the force of the jump. So I'm looking for F jump. I want to get F jump by itself. F jump minus W, and W is the force of gravity. And we should all know that W is always equal to mg. The weight, the force of gravity, is your mass times the acceleration due to that gravity. And that has to be equal to, according to Newton's second law, the mass of this high jumper times the acceleration, and the acceleration we know we can plug in right here. We were given that the acceleration has to be equal to 4 g's. So mass times 4 times g. So now I want to take this and I want to do some algebra. I have the force of the jump minus mass times gravity equals ma. I want to get the force of the jump by itself, so I'm going to add mg to both sides. In algebra, whenever you're solving an equation, you can do whatever you want to that equation as long as you do it to both sides. That's going to cancel out the mg from the left-hand side, and it's going to move it over to the right-hand side. So I end up with f jump is equal to mass times acceleration plus mass times gravity. So f jump now is equal to the mass, which was 70 kilograms, times the acceleration, which we know is equal to 4 times g, the acceleration due to gravity, 4 times 9.8, plus the mass times 9.8. So F jump, when you multiply all of this out, we're going to find a total force of this jump that's equal to 3,430 kilogram times meters per second squared, which is just equal to a newton. So our final answer is 3,430 newtons. Something important to note here is this acceleration due to gravity. Now notice that I plugged in a positive 9.8. That's because way up here in this equation, where I'm writing the forces, I am taking care of all the directions involved here by writing this negative sign here. This negative sign takes care of making gravity negative. So in force problems, typically in force problems, when you're plugging in G, you're going to plug in a positive 9.8. This is different than kinematics problems, where typically you're plugging in a negative 9.8. And that's because you take care of the directions, the directional negatives, when you're actually writing out your sum of forces. So let's see another example of a force problem. This is problem 42 in chapter 4 of the OpenStax college physics textbook. We have a 76 kilogram person that's being pulled away from a burning building as shown in this figure. Calculate the tension in the two ropes if the person is momentarily motionless, and include a free body diagram in your solution. So we're not going to draw, we're not going to show you the picture. You can go to your textbook for this, but the basic idea is that I have this person that has some mass m. And there's two ropes. There's a rope going up like this. We'll call that tension number 1. And there's another rope that's acting at kind of an angle. We'll call this tension number 2. And they give us the values for these two angles. Tension 1 is a 15-degree angle from the vertical, and tension 2 is a 10-degree angle from the horizontal. So I can write down all the things that I'm given. I'm given that the mass of this person is equal to 76 kilograms. I'm also given that the acceleration of this person is equal to 0 because the person is not moving. What I also notice is that I have two forces acting at angles. I have one angle acting up and another angle acting kind of up and over, and another angle acting kind of up from the horizontal axis. So anytime I see that, that makes me think I need to break those forces up. I need to break those tensions into their x and y components. So we're going to go ahead and do that. Tension number 1 has a little bit going up. So we'll say a little tension 1y going upwards. We'll call that T1y. And a little bit of tension going backwards. We'll call that T1x. And that gets me to my total vector T1, which is the hypotenuse of that triangle. Same thing, I can draw my tension 2 in the x direction. It's going over a little bit until I get right underneath the tip of my tension 2 vector. That's going to be my T2x. And then I have a little bit going up. Going vertically, we'll call that T2y. And that again gets me from the tip to the tail of my total vector T2. So I've broken my vectors into their two components. In this case, we have a situation where we're working in both the x directions and the y directions. So we're going to explicitly write down x and y directions, and I'm going to say that anything that's going up is positive, anything that's going to the right is positive. Anything going to the left is negative, anything going down is negative. So I can use that in writing my sum of force equations. And if I have two directions, I need to know the acceleration actually in both of those directions. So I can explicitly write out a in the x direction is equal to 0, because this woman that's hanging from the burning building isn't moving horizontally at all, hopefully. And ay, this person isn't moving in the y direction. They're not falling, the rope isn't breaking, so they're safe for the moment. So we can write down the tensions. We have those written down. We can write these in terms of components of these right triangles that we've drawn. So I have two right triangles. I have my tension 1 and my tension 2. Let's take a look at the tension 1 triangle first. So in the x direction, T1 in the x direction has to be equal to T1 times either the sine or cosine of this triangle. If I look, my angle is 15 degrees, and my x direction is actually opposite to that 15 degrees. So if I'm opposite to the 15 degrees, that's going to be T1 times the sine of that 15. And I can plug this into my calculator to find that T1 in the x direction is equal to 0.26 T1. I can do the same thing for the y direction. T1 in the y direction is now going to have to depend on where y is relative to this angle. I have my 15 degrees. I am adjacent. I'm right next to that angle. And because I'm right next to that angle, that's got to be the cosine. So T1y has to be t times the cosine of 15 degrees. I can plug this into my calculator, make sure that you're in degrees, and I would get that T1 y is equal to T1 times 0.97. So I have solved for my T1x and my T1y. I can do the same procedure for the T2x and T2y. So we've recreated our figure right up here in the upper left, and I can actually write down my y direction tensions now. T2 in the x direction, and if I look at my triangle, I can see that it's adjacent to my angle, so that's going to be equal to T2 times the cosine of 10, and T2 times the cosine of 10 gives me T2x is going to be equal to 0.98 times T2, and I can do the same procedure for T2y. T2y is going to be equal to T2 times the sine of 10, where I'm using sine because this is the opposite piece of the triangle from the angle, so my T2y is going to be equal to 0.17 times T2. Now I can actually draw my free body diagram. I've pretty much gotten it done, almost completely. I've identified the tensions that are acting on this person, but there's one other force. If there was no other forces acting, this person would be moving. There has to be a force acting to counteract this tension 1y that's pulling you up and this tension 2y that's pulling you up. The only other force that could be acting to do this is going to be the force of gravity. So we have to have weight going straight down. And now that I've written my free body diagram and identified all my forces, I can actually write down the sum of forces in both the x and y directions. So start with the x direction, and the sum of forces in my x direction has to be equal to all the forces that are acting to the right. And to the right, I see that I have a T2 in the x direction acting to the right. No other forces to the right, so the only other forces I have to be acting to the left, and that's going to be T1 in the x direction acting opposite to T2. That's going to be equal to the mass times the acceleration in the x direction. And now I can plug and chug some values in. T2x, we just solved, is equal to 0.98 times T2. And I can subtract off T1x, and T1x we just found was 0.96 0.26 times t1. And that has to be equal to mass times acceleration in the x direction, which was 0. Because this person's not moving, ax is 0, and any mass times 0 gives me 0. Any number times 0 is going to give me 0. So I'm going to solve this for t2, so I get t2 by itself by adding this 0.26 t1 to both sides. If I do it to one side, I have to do it to the other. So my t2.26 t1 cancels out, and I end up with 0.98 times t2 is equal to 0.26 times t1. And I want to get one of these values by itself. I'm going to choose to get t2 by itself. It doesn't matter which one I do. So I'm going to get t2 by itself by dividing both sides by 0.98. So I do this, my 0.98 cancels on the left, and my t2 ends up being 0.26 divided by 0.98 t1, which is going to give me basically just 0.26 t1. And something to notice here is that I now have an equation that gives me what t2 is if I only knew what t1 is. And algebraically, the number of unknowns you have tells you the number of equations you need to solve it. So here, I don't know t2 and I don't know t1, so that means I need two equations. This is my first one, so I need to find a second. And typically in these kinds of force problems, the second equation you find will go from moving from the x direction into the y direction. So let's look at what we know is going on in the y direction. So in the y direction, we can also write out our sum of forces. Sum of forces in the y direction is going to be equal to all the forces that are acting up. If we go back and look at our figure, we can see that T1y is acting up plus T2y. Both of these y forces are acting upwards, minus the weight, the force of gravity, which is pulling us down, is equal to mass times acceleration in the y direction. Now we know that this right-hand side is equal to 0. Again, that's not always going to be the case. It's only true here because acceleration in the y direction was equal to 0, because we were told at the beginning of the problem that nothing is moving. So now we can plug and chug our numbers in. We can plug in for T1y, which was 0.97 times T1, plus T2y, which is 0.17 times T2, minus W, which is equal to the mass times gravity, and that's going to be equal to 0. So what I can do is I can take the T2 that I solved for in the previous part, and I can plug that in for T2. So I get 0.97 times T1 plus 0.17 times T2, which we just found was equal to 0.26 times T1. So this is what we found in the x direction. And that's where that came from. Minus the mass which was 76, which we were given, times the acceleration due to gravity, which is 9.8, is equal to 0. Now I can combine like terms, and I can actually solve this problem. I can combine my 0.97 T1 plus 0.17 times 0.26 times T1, and that's going to give me a value of 1.01 times T1, which is going to be equal to this 76 times 9.8, which I move over to the other side by adding it over to the other side. So we should be getting good at these algebra steps. I'm going to start skipping some in some of these videos. If you're struggling with where that comes from, then you should come talk to me during office hours or make an appointment so that we can get you caught up. So we have T1. Now when we divide both sides by 1.01, we get a T1 of 737 newtons. And then I can take this and I can plug it into my x direction equation, where I found that T2 was equal to 0.26 times T1. I plug in 0.26 times my T1 is 737 newtons, and I get that my T2 is equal to 192 newtons. So that is one of the more complicated levels of problems you'll get in a kind of algebra-based physics class, but it's just following a procedure and plugging and chugging.